Hello everyone, welcome to Data Dive. Today I'll be talking about time series forecasting methods. This is the second video in a two-part series on forecasting methods. In the previous video, I covered forecasting method characteristics and the characteristics of time series. In this video, I will provide a high-level overview of the various forecasting methods and a brief discussion on choosing between the models. Alright, let's take a tour of the different time series forecasting models. We can group the models into four broad categories: the baseline methods, the classical models, supervised models, and deep learning models. Let's start with the baseline methods. First off, we have the naive method, which is as basic as it gets. Essentially, we just assume that the most recent value is the forecasted value. We could also use the average or median of the historical values. And we can make a slight improvement by using a simple moving average to smooth out the trends. You might find these approaches rather lackluster, but sometimes these are the ones that work best for a short time series. Now we've got the classical methods, and often these are the ones that will get the job done. We have a variety of exponential smoothing approaches, where each one adds a layer of complexity which improves upon the simple moving average approach. First off, we have the simple exponential smoothing model, which adds a smoothing factor with a value between 0 and 1. And this smoothing factor gives more weight to more recent values. And when that particular factor is set to 1, it actually causes the simple exponential smoothing model to be the same as the naive method. If we add on another factor that accounts for trend, we get the double exponential smoothing model. And if we add on a third factor that accounts for seasonality, then we get the triple exponential smoothing model, which is also known as Holt-Winters. Next, we have the SARIMA and SARIMAX family of models. It stands for Seasonal Autoregressive Integrated Moving Average, where the X stands for exogenous or external variables, which means that these are multivariate models. The acronym also lets you know that it considers seasonality, autocorrelation, stationarity, and the moving average. A close variant is the VARMA and VARMAX family. And these models are also multivariate. But the distinction is that you're able to have multiple related time series variables that influence each other. Whereas SARIMAX is more focused on improving the forecast of a single variable using exogenous information. There are also a number of related and advanced methods. These methods are specialized for certain situations. For instance, MSTL or TBATS are designed for forecasting time series with multiple seasonalities. The GARC and ARC models are tailored for time series with high volatility or variability, such as those in financial markets. And then there are the ADIDA or Croston models, which were designed to forecast intermittent time series. And there's some unique models such as the profit model, which comes from Facebook. This is an additive model that is capable of fitting nonlinear trends. It accounts for seasonality, and it interestingly also accounts for holiday effects. Next up are the supervised methods. The main two approaches are linear regression and forest-based methods. Linear regression is really straightforward, although it generally works best when used as a multivariate approach. Meanwhile, the forest-based methods leverage algorithms such as random forest or XGBoost. And there are some caveats for using forest-based approaches, which I plan to discuss in more detail in a future video. Finally, we have deep learning models. These are models built using neural networks such as RNNs and LSTMs. Because these are neural networks, they can take in sequences and output sequences, which allows for multi-step forecasts. An example is Amazon's DeepAR, which is built off of RNNs and also provides probabilistic forecasts. There are also more advanced models that leverage a transformer-based architecture. And unlike earlier sequence-to-sequence models, transformers use something called a self-attention mechanism to process the input data in parallel, which makes them really scalable and efficient. And the main thing to note is that all of these deep learning models can be really good, but they are more complex and can be harder to interpret or explain. And oftentimes, these models require a lot more data. Finally, it's worth noting that there is research that suggests that tree-based models are still the best for time series forecasting in comparison to other techniques such as deep learning. With all of these models and approaches, it may be hard to determine which one to use. So how can we go about deciding the best approach to take? The reality is you probably will have to experiment with a couple of approaches. But the first thing to do is to examine the time series. Plot it out and run some diagnostics. Figure out if it's linear or nonlinear. Is there seasonality? Is it stationary? And how much data do you have? The answers to these questions should help guide you towards the set of models to test. Also, in general, it's best practice to keep it simple, or at least to start simple. So it may mean just using a linear regression or maybe one of the classical approaches. Ultimately, the best model is going to be determined by the problem at hand and the nature of the data. And it might be worthwhile to ask a few important questions. First, does it actually make sense to forecast, depending on the data? Do you need to extrapolate outside of the training data? If so, it might limit some of the choices you have. And finally, some models are more complex or black box in nature. So your choice of a model may be influenced by who needs to know or understand the results. And this can, again, limit your options. I hope this video was helpful. If you enjoyed it, please like and subscribe, and I'll see you in the next one.